December 26, 2004, Thailand's west coast. A calm morning, clear sky, gentle waves. Then the sea begins to drain away as if someone pulled a plug from the earth. The beach stretches further and further. People wander out, laughing, taking photos of the strange sight. No one is running. They have less than 9 minutes left to live. Miles away, deep beneath the ocean floor, the planet has already shifted. Billions of tons of water are now in motion, racing towards these shores faster than a jet. What's approaching is one of the most powerful tsunamis ever recorded. But when scientists later studied the disaster, something didn't make sense. The waves were far larger than anyone expected. The beach is gone. The people are gone. Months later, scientists checked the data. Their models predicted waves around 10 feet high. In reality, the waves were 3, sometimes 10 times larger. So what happened beneath the ocean floor that morning? The trigger was invisible. The mechanism was hidden. By the time the effect became visible, it was already too late. So what moves the water with enough force to cross entire oceans and destroy coastlines on the other side of the world? Beneath our feet, the ground feels solid, but it's not. Earth's outer shell is broken into giant puzzle pieces called tectonic plates. Slabs of rock and crust, some as big as entire continents, floating on a layer of slow-moving, semi-molten rock beneath them. Like massive icebergs drifting on a thick, sluggish ocean, except this ocean is made of stone hot enough to glow. This deeper layer is called the asthenosphere. It behaves like slime. Pull it fast and it snaps. Apply slow, steady pressure over centuries and it flows like thick caramel. Heat from deep inside the planet stirs this layer, dragging the plates above in a slow, grinding dance. Most of the time this movement is imperceptible, a few inches per year, slower than your fingernails grow. But off the coast of Sumatra, 2 plates were locked in a deadly embrace. The India Plate, a massive slab carrying the Indian Ocean, was sliding beneath the Burma Plate at about 2.36 inches per year. Subduction, geologists call it. One plate diving under another, sinking back into the mantle. But it doesn't slide smoothly. The plates stick. The edge of the Burma Plate gets dragged down, bent like a diving board with someone standing on the end. Pressure builds. Years become decades. Decades become centuries. For over 200 years, the Burma Plate bent deeper and deeper, storing energy like a massive compressed spring. On December 26, 2004 at 7:58 AM local time, it snapped. The rupture was catastrophic. The seafloor tore open along a fault line 807 miles long, longer than the distance from New York to Miami. The Burma Plate lurched upward, rebounding from centuries of compression. In some places, the seafloor rose in seconds. The ocean above didn't have time to flow around it. Billions of tons of water were suddenly displaced, thrust upward, forming a vast bulge on the surface. That bulge began spreading outward, not as water rushing forward, but as energy moving through water. In deep ocean, a tsunami can race at 435 miles per hour, jet speed, yet remain almost invisible. Its crest rises less than 2 feet above the surface, and ships pass over without ever knowing. By the time anyone realizes it's there, it's already too late. 6 months after the 2004 disaster, scientists at NASA's Jet Propulsion Laboratory are staring at a problem. The Sumatra earthquake lifted the seafloor by about 16 feet. Scientists ran the numbers through their tsunami models. The forecast. waves roughly 10 feet high at distant coastlines. Then the data met reality. In some places, the waves reached 30 feet. In Banda Aceh, nearly 100, 10 times higher than the models predicted. They pull up the raw GPS data again, and there it is, something everyone had missed. The seafloor hadn't just moved up 16 feet, it had lurched sideways by up to 66 feet, along that same 800-mile scar on the seafloor. For decades, scientists assumed horizontal motion was irrelevant for tsunamis. Vertical displacement creates waves, and horizontal motion doesn't matter. They were wrong. Think of a car slamming on its brakes. The car stops, but everything inside keeps moving forward. When the seafloor lurched horizontally, it dragged billions of tons of water along with it. That sideways motion added massive energy to the wave. They run new simulations including both vertical and horizontal displacement. The new prediction, about 33 feet, in some places close to 98 feet. It matches. The discovery revolutionizes tsunami science. The horizontal shove matters massively. The strange thing is this: the water itself isn't crossing the ocean. A tsunami is energy moving through water, not water travelling forward. Take a rope stretched between two people, snap one end up and down. A wave travels along the rope to the other person, but the rope itself doesn't move forward. Each part of the rope just goes up and down in place, passing the energy to the next section. A tsunami works the same way. The ocean is the rope, the energy is the wave. By the time that energy reaches land, it's carrying the kinetic force of an entire ocean behind it, even though the water started thousands of miles away and barely moved at all. So what would you actually see if you were out there? If you could place a marker, a buoy, a ball, even a drop of dye on the surface of the ocean, it wouldn't ride the wave across the sea. It would bob gently up and down, tracing a small circle as the wave passed beneath it. Each molecule of water is just passing the message along to the next. By the time you see the wave coming, the energy that will destroy your city was set in motion hours ago, possibly thousands of miles, and there's nothing you can do to stop it. A fishing trawler bobs gently in calm seas 31 miles off the coast of Sri Lanka. One fisherman notices the boat rise slightly. A long, slow swell that takes nearly a minute to pass. Not unusual. The ocean breathes like this sometimes. The wave is stretched over hundreds of miles from the trawler's perspective, just a gradual rise and fall. Like sailing over a hill so wide you can't see the slope. That hill is carrying the energy of thousands of atomic bombs. At that moment, the energy passing beneath them is 45 minutes from killing 35,000 people on the Sri Lankan coast. 45 minutes later, when the crew tries to return to port, their village will be gone. This is how tsunamis move, like silent freight trains beneath the surface, smooth, fast, almost invisible. Then they approach land and everything changes. A speeding train suddenly hitting an uphill climb. The ocean floor slopes upward beneath it, forcing the wave to slow down. But the total amount of energy it carries doesn't decrease. For example, squeeze a water balloon. The water has nowhere to go but out. The balloon bulges, distorts, eventually bursts. The tsunami does the same. Squeezed by the rising sea floor, it has only one direction left: upward. This moment is called shoaling. The wave transforms, its speed drops, its length shortens, and its height skyrockets. What was once a gentle swell barely knee-high in the open ocean can rise into a wall 30, 60, even nearly 100 feet tall as it approaches land, higher than a 3-story building. Then the shoreline itself becomes a trap. Bays, harbours and inlets focus and amplify the wave's energy, funneling it into ever higher surges. In some places, the first sign of disaster is the sea draining away. the trough of the tsunami arriving before the crest. In others, the wave simply appears on the horizon, immense and relentless. What was once an invisible pulse of energy is now a roaring wall of water. When it hits land, the physics multiply. The wave doesn't just push forward, it churns. Water rushes inland at highway speeds, but it's not just water anymore. It's a slurry of destruction. Cars, boats, shipping containers, entire sections of buildings, all churning together in a mass that weighs thousands of tons. Each piece of debris becomes a battering ram. Entire buildings are lifted from their foundations. In 2011, cars were swept onto rooftops in Sendai. Ships weighing thousands of tons were carried kilometers inland. In 2004, coral reefs were ripped from the sea and thrown half a kilometer from shore. Long after the first wave has passed, more keep coming, sometimes hours apart, each one carrying new wreckage, each one adding to the devastation. Then comes the backwash. When the water finally recedes, it doesn't just drain away. It pulls everything back out to sea. People, cars, the wreckage of homes. The ocean takes as much as it gave, dragging the evidence of civilization back into the depths. Tsunamis rewrite coastlines, they redraw maps, they leave behind poisoned water, shattered infrastructure, and landscapes scarred beyond recognition. Recovery takes decades, and for many communities the scars never fully heal. If a tsunami is unstoppable, then the only hope is to see it coming and move before it strikes. But in 2004, no one was watching. The Indian Ocean had no tsunami warning system. When the magnitude 9.1 earthquake struck off Sumatra, seismographs around the world detected it within minutes. But detecting an earthquake and predicting a tsunami are different things. Scientists at the Pacific Tsunami Warning Center in Hawaii knew something catastrophic had happened. They tried to reach governments around the Indian Ocean, Thailand, Sri Lanka, India, but there were no official channels, no protocols, no way to confirm what was coming. In Thailand, no warning reached the public, no sirens, no evacuation orders. The beaches were full. 2 hours after the earthquake, the wave struck Thailand's coast. Thousands of lives were lost. That failure changed everything. Within months, nations committed to building a warning system for the Indian Ocean. Sensors deployed, communication networks established, evacuation protocols created. And when Japan, which already had one of the world's most advanced systems, faced the 2011 tsunami, the world watched to see if preparation could really save lives. Today, a network of sensors lies hidden beneath the ocean, anchored to the seafloor, tripwires on the ocean floor, so to speak. The moment a tsunami passes overhead, they feel the pressure change and send an alert from the seafloor to a buoy, from the buoy to a satellite, from the satellite to emergency centers around the world. A relay race against the wave itself. If the system works, the warning arrives minutes or hours before the water does. Minutes that mean the difference between a mass evacuation and a mass grave. March 11th, 2011. Off the coast of Japan, the seafloor lurches. Within 3 minutes, sensors detect the earthquake. Sirens wail across coastal towns. In Kamaishi, a small city at the northeastern coast, school children have practiced this drill dozens of times. When the alert sounds, they run, up the hill, away from the shore. Their teachers follow. 30 minutes after the earthquake, the wave arrives. It obliterates their school, tears it from its foundation, scatters the debris across the town. The children are safe, every single one. Nearly 3,000 students survived, but across Kamaishi, over 1,000 residents died that day. Across Japan, nearly 20,000. The warnings reached them. Many didn't evacuate. Some couldn't move fast enough, others searched for family members. Some trusted seawalls that collapsed. The children had been trained not just to evacuate, but to run immediately without hesitation, even if adults around them didn't move. The warnings worked, but warnings only save those who act on them. That's what minutes mean. Modern systems go even further. Networks of GPS stations track the movement of the Earth's crust itself, measuring both the vertical heave and the horizontal slip of the seafloor in real time. By combining these measurements, scientists can estimate a tsunami's size and direction before the wave has even travelled far from its source. Not a crystal ball, but close. Japan took it even further. After the 2011 disaster, Japan launched a massive coastal defence build-out. Today, roughly 270 miles of seawalls run along the northeast Pacific coast, with many segments rising nearly 50 feet high. But the 2011 tsunami tested every defence. Some walls held, some didn't, proving that no wall can ever guarantee safety. But the warnings worked. Thousands evacuated in time. The walls bought minutes, the warnings saved lives. We can't stop the Earth from moving, we can't hold back the ocean, but we can understand them, and with understanding comes resilience. The goal isn't to defeat the sea, it's to outpace it. Since 2004, the world has invested over $4 billion in tsunami preparedness. The Indian Ocean now has 26 detection buoys where there were once 0. Indonesia, Thailand and India built dedicated warning centres. Japan rebuilt 250 miles of coastline with evacuation routes marked every quarter mile. We learned something in 2011 when the children of Kamaishi ran up the hill and lived. Understanding beats walls, warnings save more lives than concrete. The next tsunami is already forming right now, somewhere beneath the Pacific, or the Indian Ocean, or the Mediterranean. In some subduction zone we've mapped but cannot control. Plates are locked, pressure is building, the Earth is bending. The question isn't if it will break, the question is, will we be ready? Will the sensors detect it in time? Will the warnings reach the coast? Will people listen? Will they run? That's the only battle we can win, not against the ocean, against denial. The 2004 tsunami took 230,000 lives because there was no warning system. The 2011 tsunami took far fewer because there was. The difference wasn't the wave, it was preparation and science. The planet will keep moving, the waves will keep coming. Whether we survive them depends on how much we've learned to listen and how seriously we take what science tells us. The ocean doesn't rage, it doesn't punish. It moves according to laws older than civilization itself. If we're wise, we'll build our future with that truth in mind, not as a threat to conquer, but as a reality to respect. The ocean doesn't ask permission, but it rewards those who pay attention and trust the science that helps us understand it. The same forces that can move oceans can also reshape continents. When tectonic plates pull apart, the crust stretches, cracks and sinks. Given enough time, that process can split a continent in two and create a new ocean. It's happening right now in Africa, where the birth of a new ocean can already be observed. Watch this video to learn how it's unfolding.